Hello, so today we are going to do this problem, which is part of Leetcode daily challenge, as far from land as possible. So the problem says we get an n by n grid that has values of 0 and 1. And 0 basically represents water, while 1 represents land. Okay? And what we want to do is find a water cell such that the distance to the nearest land cell is maximized, right? So we want to find a 0 such that the distance to the nearest one is the maximum possible, okay? And we want to return that distance, okay? So basically the water that has the closest land, the distance to the closest land, the largest possible. And by distance here, we'll use Manhattan distance, which is going to be just the difference between the x values and the y values, right? So you can think of it as, let's say you have 2 points, maybe one is here and then another one is here, then the Manhattan difference is going to be the difference here, so on the x-axis, plus the difference here on the y-axis, okay? And so for example, with this one here, we have this cell, right? And then we have, so basically we want the distance for the waters. So if we take a look at, for example, this water here, this one has the furthest possible one being this one, and all the sides have the distance, the Manhattan distance of 2, because we said it's the difference on the x-axis and the y-axis, so it's 2. All the other ones have the distance being just 1, because this one is 1, this one is 1, this one is 1, you get the idea, except this one is 2. So that's the highest possible one, that's the highest possible distance, so we return that. Now if you take a look at the constraint here, you can see that it's only up to 100 on the length. So how do we solve this? Okay, so let's see how we can solve it. So let's just go back a little bit to the goal of the problem. So the goal is to find for waters to find a water cell such that the distance to the nearest land cell is maximized, right? So basically the 2 water and land cell that have the maximum distance, with the condition that that land is the nearest possible, right? So for example, here I'm just trying to visualize it for you. Let's say we have 0, and then the closest one is this one, and then we have this water, the closest one is this one, this water, closest one is this one. We want to take this one, the furthest one. So that's what the problem wants us to do. Now, how do we accomplish this, right? So if for each, before just considering this maximized, what we want is basically for each water, we want to find, right, for each 0, we want to find the shortest path to a 1, right? That's what we want to find. And then we want to do it for all of them, right? Shortest path to a 1 for all the positions that have value 0. And then among all of these, we want to get the distance. Let's say this is distance 1, we get distance 2 here, and then this is distance, let's call it I, right? And so what we want, the result, because we want the distance maximized, and that's also visualized in what I have here, what we want is just the maximum out of these, all of these distances, right? So that's the idea. Okay, so now you might say, okay, let's just do that actually, because with shortest path, we know that we can do it with BFS, and we know BFS on a graph, and for our case here, the graph is going to, the nodes are going to be just the cells, and the edges are just going to be the moves you can make. Let's say you can go left, you can go down, you can go up, you can go left or right, okay? So those are the moves. So we know how to do these. X plus 1y, x, y plus 1, x minus 1y, you get the idea, right? And so this should be feasible, right? To just take every 0 value, do a BFS, and find the shortest path to the nearest one, and then take all of these and get the max. So that's the first approach here. that I call forward approach, which basically is find the nearest land for each water and then just take the max. However, if you try this approach, you will get time limit exceeded because you will do multiple BFSs, and if you try it, you'll get multiple BFSs, and you will do a BFS for each water. So the question becomes, how do we combine them? How do we do just one BFS so that we can cut the time? And that actually you need to just think a little bit different. So here we are doing a forward approach. Let's think about just doing a backward approach then. And so the backward approach will say with BFS, I think the problem is most people think about BFS as just a way to find the shortest path from a source node to a source destination. That's what most people think about it for. But it's not just that. Another usage for BFS is you can find a level by level traversal for BFS, right? That way, if you are going from some type of values, let's say here we are going from land, let's say if we are going from ones, we can try to get to all the possible zeros, right? And the last one we get to it, this is going to represent the max distance, the max possible distance, right? And so this is the approach that we are going to take here, okay? Is the approach of using BFS instead of from a source to destination, from multiple sources, because we take all the land to cover all the levels, because we want to reach all the zeros, okay? And this is what's called multi-BFS, multi-source BFS, okay? And so what we are going to do is, as I said, is just using our BFS here. We'll pick all the land positions, right? So all the land positions. So those are going to be our first level. And then the zeros immediately reachable by one distance. So just by doing just the next one edge, immediately reachable. Those are going to be, let's say, so this is going to be level 1, this is going to be level 2, and then once you get here, you can go to the next level of zeros, right? So they have nodes reachable from these, and then level 4 all the way until the last 0, okay? And that will give you if we take that distance, that will give you the longest possible distance for the furthest reachable zero from a land, right? And so that's sort of the idea. And by the way, we will stop. We won't just cover all the zeros, right? We will stop if for zeros that are not reachable by 1, we won't go to these, right? So that's why also we get the nearest requirement here, not just that the distance is maximized, right? Okay, so I hope that made sense. So that's why we will choose this backward approach. Now let's see how it will work. So we'll go level by level. So for example, first we have our matrix graph here, right? So I have the initial land positions at value 1, okay? And so the first step, right, we do the first BFS level, which is just going to go through the immediate neighbors, right? That's what BFS does, is you start from a source. And in this case here, we start from multiple sources, 4 here. And we go to the immediate neighbors. And then from there, we add those to the next level. And then from those, we go to the neighbors of those, right? Except here, just for our visited set, instead of using a visited set to mark visited, we will just mark the node that we visit, we will mark it with 1. Because we in the first initial place, we make all the sources be 1, we already saved those. And so if we mark those with 1, it's just going to serve that when we check a neighbor, if it has value of 1, we are not going to include it in our level, because that means it's already visited, right? So we'll mark with 1 to mark visited, and I just did it here with different colors to show you. So for the first level, we just have these in our BFS level, and then for each of them, this we go here. For example, for this one we can go here as well. This one goes here, this one goes here, this one goes here, this one goes here. So all of these positions now become 1 because we traverse to them in the next level for BFS. So those are the ones I marked in yellow here. And so now we are in level 2. It's important that we are counting at which level we are. And so now for the next step, so now once we have those, well, this one is we go to here, this one we go to here, and so we mark those 2 as well. And now since we marked everything, there is no longer any cell that has a value of 0. Okay, that means our level now is empty. We stop. Now one thing just to confirm and show you that this answer that we got, which is 3 minus 1, which is 2, is actually the right answer, because if we take a look, this water at this position 0, the closest land is actually either this one or this one, and these have distance 2, right? And that's, you can see it here, it's the last one we visited in the last level because it has purple color here. Okay, and so we actually arrived at the right solution with this example. Yeah, so basically this one is 2, we arrived at 2 here, and this is the water that has the distance between it and the nearest land maximized is this point here. Okay, and similarly for this one that we also colored this color, which is the last one, the distance between it and the nearest one is either this one, which is 2, or this one, which is 2, or this one, which is 2, this one, which is 2 again, and then you get the idea. Yeah, so the nearest one, the nearest land to it is always 2, which is the answer here, and that's why we colored it here. So you can see this solution actually solves the problem. One special case we want to handle is what if we have all 1s, so we will never, so all either all land, so no water to start with, or all water and no land, so no solution either. So in both these cases, because we start our levels with 1 here, we'll end up with 1 for levels, and so when we do minus 1, we'll end up with this here being levels minus 1 being 0, right? And that's not the right answer we want to return, because here there is no answer, it should be minus 1. And so for that cases, we're just going to check. If it's bigger than 1, then we use this. If not, there is no solution, so we return minus 1. So this is just a special case we need to handle. But other than that, this solution should work. So let's implement it and make sure it passes test cases. Okay, so let's implement the solution we just saw in the overview. So what we need first is we need to start our BFS from all the land positions, which is from all the 1's values. And so to do that, we want to just go through all of them. So I in range of, this is going to be rows, and we will need to store how many, the size of the number of rows and the number of columns. So it's going to be just the length of the grid and the length of the number of columns. And then we are going to do the same for columns here. And now we are going to check if the grid at this position ij is equal to 1, so this is basically land. We want to start from all the land. We are doing the backward approach. And so for our BFS, we'll just initialize the first level, right, with an array here, and we'll add to that level here I and j, the coordinates. Okay, and now with we'll start our BFS, we'll just have the overall number of levels, not the single level. And we said we want to return levels minus 1 if it's a valid solution, but if not, we want to return minus 1, because otherwise we'll end up returning 0. Okay, so now we do our BFS, which goes through level by level. So we'll just, this here we'll store the next level. So for the next level, we'll store the values for the next level. because for those we want to go through the neighbors, right? And so we'll go through the neighbor here for each level coordinates. So in level, this is just normal BFS that is done level by level. And so for the neighboring coordinates, we said we can go up, down, left, right. And so that's what we'll do here with the coordinates. So x plus 1y, this is for right. And then x, y plus 1, this is for down. And then x minus 1y, this is for left. And then x, y minus 1, this is for up. Okay. So these are all the possible coordinates. So first, we of course need to make sure the coordinates are valid. So we can do that like this. And we need to make sure that the cell has not been visited yet. And what we said in the overview, when we visit a cell, we will mark it with the value 1. And so since we traverse from lands, we traverse forward to water, so to 0 values, we just need to make sure that its value is 0 because we only are going to water. We already did add all the lands here and we are going only to water, so value is 0. So only if the value is 0 that we go to that we added to the next level. But we also mark it as visited, so we mark this cell. So we don't visit again, we mark it with 1 so that next time it will fail this check, right? And we need to add it, of course, to the next level, which is appending just an x and an y. Okay. So sorry, I forgot here j. Okay. And so now that we started in the next level, we need to copy it. We need to say to level that it's equal to the next one. Okay. And now we just need to, each time we do a level, so we just processed a level and we are going to the next one, let's increment it. Okay. And so at the end, we will just return that. When we reach the end, this level will be empty. Okay, so if we run this, submit. So you can see this works fine. So this is just BFS level by level. And we are doing multi-source BFS because we are not just adding one source, we are adding multiple here, all the land positions. And the other thing that is unique with this BFS is we are not just looking for the shortest path, so we are not checking for a destination here. We want to go through all the graph, all the water positions, level by level, and that's it. And we want to just get the max one, the furthest level we can reach, right? And that's the idea pretty much. Yeah, so that's pretty much it. Please like and subscribe and see you on the next one. Bye.